Another function that we met, it's the natural exponent. As you know, if I take e to the power of x and I try to derive this function, I will get exactly the same function. This is a property of the natural exponent that means that now if I have to solve an indefinite integral with e of x in the x, e of x as my integrand, then the result is simply going to be e to the power of x plus a generic constant c, where c belongs to the real numbers. It's very easy to remember that it looks the same and actually gives the same function. Other functions that we have to talk about are actually the trigonometric function. Trigonometric functions that we're going to study are actually the sine of x and the cosine of x, not the tangent. So we have to remember that if we take the derivative of a sine function, what we get is actually a cosine function. And if we take a derivative of the cosine function, we get actually minus the sine function. So it goes by itself that the integral of the cosine of x in the x is just going to be the sine of x. This is its antiderivative plus a generic constant k1, where k1 belongs to the real numbers. And the derivative of the sine of x in the x is just going to be minus, I am moving this minus on the other side, on the left hand side, it's going to be minus the cosine of x plus another constant, now I will call it a, where a is also a real number. One last function, if you want, that we didn't really study, but that it's worth noticing maybe more as a comment, is that if we derive just something that looks like a constant k times x, so let's say we have a function g of x that looks like k times x, well, the derivative of g prime of x, it's going to be just k. So it means that the integral of a generic constant k times dx, k can be anything, it can be a number, but it can also be just a symbol that it said in the question it's a constant. This integral, it's equal, or the antiderivative is k times x plus a generic constant that I will call now c1, where c1 belongs to R.